Hi everyone. For today's class, we will talk about this mathematical preliminaries. So this is our third lesson for this course. So we discussed the two lessons already. The first lesson has to do with um, introduction to data analysis, right? And the second lesson is data science. So more general, I mentioned. This one is more specific, but still, you might get overwhelmed. Though the first part is a review, but still, some topics will be discussed, no? Topics related to data analysis, okay? And also the second part. The second part, you might be familiar already. The word matrix, no? The array of numbers, no? Row of and column of numbers. Okay, class? So anyway, so let's go to the first part. So which is about sets and relations, no? So again, you discussed this already in high school or even in elementary, right? So set is a collection of objects referred to as elements, which are assumed to be distinct. So elements or members of a set, no? So that's what we call them, no? And we denote this, we put these elements inside this grouping symbol, which we call braces. Okay, class? Here, class, collection of objects. So meaning to say, we're not just talking of set of numbers, no? We can have like names of persons, names of places, no, or letters. Okay, or we can even have ordered pair. Okay, you know ordered pair, class, right? The ordered pair. For example, I think you learned that in algebra when you talk of the Cartesian plane. There is a point. You can plot a point, and that point is represented by an ordered pair, the x coordinate and the y coordinate. Because in a Cartesian plane, you have the x-axis, the y-axis. That's why it's possible. And those x and y-axis, you have numbers there, real numbers. That's why if you plot a point, we can have real numbers for the x coordinate and the y coordinates, right? For example, 2, 3. That is an ordered pair of real numbers, no? But we use parenthesis, class. Not this, no? I believe you know what I mean by parenthesis. Not this braces, no? There's another one, bracket, no? But here we will use braces for the set and then parenthesis, no? For the ordered pairs. We'll discuss this, no? Again, review of this ordered pairs. Okay? And when we talk of set, we can talk of empty set or null set or void set. So this is a set with no elements denoted by this. So no element, that's why it's denoted by this. Okay? So we call it empty set, no? Null set, void set. But I think you're familiar with subset also, right? So subset of a set. So for example, A is a subset of B. So meaning to say all the elements in set A can be found in set B, right? Because subset, no? Actually, empty set is also a subset of any set, right? You learn that empty set is a subset of any set. Okay? So I think the next one is equal sets, no? Equal sets having identical elements. So I think self-explanatory. If you have exactly the same elements, so if you have the same elements, exactly the same elements or members in the sets, for example, you have 2 sets, 3 sets, and having identical elements, you call them equal sets. You can have different order. It doesn't matter. For example, you can have a set of set with elements 1, 2, 3. So 1, 2, 3 is the same element as the same set as 3, 1, 2 or 3, 2, 1. So different order, but all of them equal sets. And all of them contain 3 elements. But it's possible for you to have the same number of elements, but not equal, right? Because the elements are not exactly the same, not identical. Probably for some, but if there's one like different from the rest, still not equal sets. For example, if you have 1, 2, 3, and then all of a sudden you have 1, 2, 4. Yeah, they have common elements, but they're not equal elements. They just have intersection. The intersection of these 2 sets is the set containing 1, 2. But they're not equal sets. And if we have 2 sets with intersection, we have joint sets. We call it joint sets, no? So in meaning to say, these joint sets are no intersection, sets having no common elements. So my example a while ago, the 1, 2, 3, the 1, 2, 4, joint sets because they have intersection. Okay, they have common elements. In fact, a subset and the set are joint sets. It's just that the intersection is the subset. For example, A is a subset of B. We can say that A and B are also joint sets. No? They are joint sets. But to be more specific, we can just say A is a subset of B. Okay? But they're joint because they have common elements. It's just turned out that the common elements are all the elements in the subset. No? Whereas this joint sets class, no common elements. No? But it's possible for you to have joint sets, like the examples I gave to you, that not really subset. No? As long as they have common elements, they don't have to be common in like the set in A. All the elements in set A you can found in set B. No, you don't have to be like that for it to become joint sets. No, in that case subset, but subset in the case joint also. Okay, so I think this is clear. This is just to understand. If we talk of, for example, the set of real numbers class, the set of real numbers you can divide it into two disjoint sets. No, two disjoints. That when you take the union of these two disjoint sets, we have all the real numbers. No, so disjoint because they don't have intersection, they don't have common elements. And what are these disjoint sets? In the set of real numbers, they're actually subsets, no, of real numbers. This is the set of rational numbers and the set of irrational numbers class, right? When you say set of rational numbers you can put it into fraction, whereas irrational numbers you cannot put it into fraction. Okay, let's put it in decimal form first before the fractional form. For example, the decimal 0.35. 0.35 is a rational number because you can put it into a fraction, 35 over 100. Even 2 is a rational number. You can put it into a fraction, 2 over 1, 4 over 2, and so on and so forth. Even the negative, right? The negative 4, you can think of it as negative 4 over 1, and so on and so forth. Okay, so any number that you can change to fraction is a rational number. That's why in decimal form, you can think of it like terminating decimal or repeating. If it's terminating, just like the 0.35, no, it stops, and it has an equivalent fraction, 35 over 100 or 7 over 20. Okay, you can have a decimal number of long decimal number, but it stops like let us say 0.33333 up to the 1 millionth no position. Okay, it's long, right? It's long, but since it stops, it's terminated, it's still a rational number. You can change it to fraction. Okay, but we have another one which doesn't stop but repeating, just like the 0.33333, but it doesn't stop. It doesn't stop. That one also is a rational because you can change it to fraction. It's equivalent to 1/3, no? But that's not equal to the other one class, although it's 0.33 also, but it stops. It stops from where? For example, 1 million position. Still not equal to that other one, the 1/3. The 1/3 is the one that doesn't stop, 0.33333, and it goes on. It doesn't stop. That's 1/3. So what I'm saying is that in decimal form, you have a rational number when you have what? Terminating decimal number, it stops, or repeating decimal number. Okay, whereas in irrational number class, if you put it in decimal form, you try square root of 5. Use calculator. What is square root of 5 in calculator? It stops, right? Because the space there is limited. However, you cannot see the pattern. There's no repetition, right? There's no pattern. No? But if you print it using a laptop, using continuous forms, meaning to say there's this paper, like it's a long, like continuous forms, no? If you continue printing the value of square root of 5, it will not stop unless there's no power, no? There's no power in your laptop, no? It will stop. But if you just continue it, it will never stop. Even if, as long as you have the paper, no? The continuous form, even if you reach like 365 days or more than 365 days or 100 years, if you continue doing that, it will never stop. That's square root of 5, and there's no repetition. So it's like kind of different from the 0.3333, which also doesn't stop, but there is a repetition. In fact, we can shorten it. The 0.33, we can shorten it using what do you call that? The ellipsis, the 3 dots, dot, or the vinculum. The vinculum is the horizontal segment that you put on the repeating digit. For example, if you don't want to make it like 0.3333 and then use ellipses, you can just say 0.33. but you put the vinculum on top of the 3. It's understood repeating, and that's equal to 1/3. Whereas the square root of 5 class, there's no symbol that you can use to really show the exact, no? You can what do you call this? Round it off, but it's not the exact. Okay. So what I'm saying, if it's like irrational number, it is non-terminating and class A and non-repeating. Both conditions should satisfy for it to become irrational number. Whereas in rational number in decimal form, or it's either terminating, it stops, or repeating. Okay? That's how you distinguish rational and irrational. Now, if you think of these conditions, you'll never have a common element between these two sets. That's why they are disjoint sets. No? You'll never have because of these two conditions. Okay? Square root of 7, usually the radical class, the radical. Square root of 7, but of course, square root of 4 is rational because that's equal to 2. But there are other symbols class, like the pi. The pi, yeah, that's also irrational because that 3.1416, it doesn't stop also actually. And there's no repetition, there's no repeating pattern. However, we just use 3.14 for convenience, right? We round it off, but it's not the exact value of pi. That's why, since there's no exact value, we use a symbol, pi. That's the exact pi. But if you want to put it in decimal form, you can just approximate it. Sometimes we say 22/7. Those are like approximation. They're not exact. Okay, so pi is also irrational number. No? So I believe you understand this joint sets. No? I think even without that example, you understood already. No? It's just that I mentioned real numbers. No? Because later, we'll use real numbers also in the second part. No? But of course, in data analysis, it's possible you don't use only your data as real numbers as data. No? Other data types you can have. No? Other than the real numbers. Okay, class? So I think you understood this concept. And then now, this is interesting concept, again, related to sets, Cartesian product. Probably this is your first time to hear this. But interesting operation. We can call this operation on two sets, right? On sets, because the operation that you know on sets are what? Union, intersection, difference. No? Okay, and then this one is another. It's like multiplication, right? Cartesian product of two sets. Set of all the ordered pairs. So again, the ordered pairs are here now. Of sets X and Y. But I want you to put this into context, no? Because usually when we talk of ordered pairs, especially in algebra, we deal with real numbers because we discuss ordered pairs in the context of Cartesian plane, where the real numbers are used there, right? In the Cartesian plane. But this one class, in the context of data analysis, we can use not just numbers. If you'll notice, we have letters, no? Okay, so that's the context we are in. Huh? Okay, so when we talk of this Cartesian product of two sets and then ordered pairs. Okay, now this is easy to understand, class, with the example. Look, you have here two sets, then this one numbers and letters. No, so if you want to get the Cartesian product, so X cross Y is equal to the set. So it's a set, class, no? So XY, so meaning in the ordered pair, so you have here set of ordered pairs now. Okay? Set of ordered pairs. So you notice these are the parentheses we use. We use parentheses, no? And then for the set, we use braces. Now for the ordered pair, we use parentheses because order matters. 1A is different from A1. 1B is different from 2A is different from A2. 1B is different from B1, no? So in ordered pair, that's why ordered, no? Sometimes we can also talk of triple ordered pair. There's ordered triple. I'm sorry. Because when you say pair 2, ordered triple, now we can also talk of that. But this one is ordered pair. That's why 2. So here, class, for the first, we get it from here. For the first, for the second coordinate, we get it from this, because X cross Y. Now, if it's Y cross X, for the first element or for the first coordinate of the element, we get it from Y. Okay, so the order matters here. So in a way, in Cartesian product, we can talk of commutative, just like real numbers. So they're not commutative. No? X cross Y is not equal to Y cross X. No, they're not commutative. Actually, later on, class, in vector algebra, we have this property also, but we will not go into that. But what I'm saying is, we can talk also of commutativity, associativity, no, in the second part, but we will not tackle them, just to give you an idea. Instead, what we'll tackle in the second part is the operations, no? The addition, multiplication, no? And other operations. No? If we have these operations, probably you will think of the properties, not such as commutative. Is it applicable? Actually, there are lessons on that part, but I don't think we will discuss them here. Okay, so now going back to this class, so if it's x cross y, that's easy to understand, right? 1a, so we have here 1b, so we have another one, 2a, and then 2b. That's all. Now for y cross x, you start from here, a1, a2, b1, b2, and we have here. The order does not matter, class, huh? But we follow that order so that we're sure we're able to list down all the possible elements for this Cartesian product. No? That's why we did that pattern. No? But the order does not matter here because it's a set. No? If it's an ordered pair, yeah, the order matters. No? But in a set, as I mentioned, equal sets, as long as exactly the same elements, but different order, they're equal sets. But in this case, class, they're not, right? They're not. They're not exactly the same. So they're not equal sets. As I mentioned, even if like they're common to some elements, but there's one, they're not the same, automatic, they're not equal sets. But in this case, as in all of them, they're not the same, right? You cannot like find an intersection between these two. There's no, in a way, we can say that this is what? Disjoint, no? There are disjoint sets, no? Because they don't have common elements. Okay? So anyway, but the focus here is the Cartesian product of two sets. I just illustrated the other concepts on set that we discussed a while ago. Okay, this one also is interesting. Actually, relation, you learned this also in high school already. Remember relation and function, class? But relation, what you learn in high school is the set. It's a set of ordered pairs. Actually, this one is still set of ordered pairs. It's just a different way of defining it. Elements of the first set relate to the elements of the second set, but actually still ordered pairs. Because in high school class, when we talk of ordered pairs, again, in the context of real numbers, but in this one class, it's more general. No? That's why first set relate to the elements of the second set. So meaning to say, it's possible we do not deal with real numbers only. The sets are not only real numbers. No? Can be other collection of objects. No? Okay, that's why, but yeah, we can still think about relation as set of ordered pairs. Now, how does it differ with function? I have to mention function this time because later the function will be mentioned also. So it's better that we distinguish between the two. What's the difference between relation and function? We know that, right, in algebra, all functions are relations, but not all relations are functions. In a way, in terms of set, we can think of function as a subset of relation. Because when we define function, it's also a set of ordered pairs. But there's a special condition, property that this relation has so that it's called, it's given a different name. Instead of just relation, we call it function. Okay, but relation class, it's more general. So it's more like a universal set. So relation is just set of ordered pairs. Okay, so what is this thing that differentiates a relation, a function from any other relation? Okay, let's give a specific example. And this time, let's have the elements, real numbers only, so that easy to understand. For example, this simple example of a set, a finite set. You have 1, 2, ordered pair. Ordered pair 1, 2, then another ordered pair, 1, 3. Okay, then we put these two ordered pairs in braces. So we have a finite set. A finite set with two elements. It's just that the elements or members of the set are ordered pairs. Okay, so 1, 2, 1, 3. So what can you say about that set? Is it a relation or a function? Remember, relation is a set of ordered pairs. A function is also a set of ordered pairs. It's a special. There is something in the function. That's what I'm trying to ask you. Is that something in the function that differentiates it from other relation? Okay, what is that? So to answer that question, first, yeah, that example, what can you say about that? What do you observe? 1, 2, 1, 3. They have the same, these two ordered pairs have the same what? First element, what do you call this? The first coordinates, no? The first coordinates. Both of them have 1, no? In the first coordinate, no? If that is the case, so that means it's not a function. Okay, I think you know that, no? But if they're different, it is a function. So that's what makes the function different from any other relation. For that relation to become a function, the ordered pairs, no? For this example, you only have 2 ordered pairs. But if you have more, the condition is that all of them should have different first coordinates, no? The first coordinates, or the x. If we're talking of real numbers, the x values. If we're talking of real numbers, the abscisses, right? We call them abscisses, no? All of them should be different. If we can spot 2 ordered pairs with the same x values, then automatically, even if the others are different, automatically that relation is not a function. Okay? So later, though, just to review the concept of function. So for now, just focus on relation, the more general concept. Now we can even make it more particular. We can talk of binary relation R. This one is also interesting. A subset of the Cartesian product of the two sets. Subset. No? So again, let's go back to the Cartesian product class. No? The Cartesian product of the two sets, so that we can talk about this binary relation. No? Which we denote as capital R, but we can use other symbol. So relation, then it becomes binary relation. So if it's a binary relation, it's a set of ordered pairs, right? Okay, so let's go back to the Cartesian product. So this one class, okay? So this Cartesian product X cross Y, we have here binary relation in a way, right? Because when you say binary relation, just subset, right? Subset. So we have subsets. What subsets are possible here? We have a set containing one element only. So we can have 1A only, right? But of course, this 1A ordered pair. So you put it in a parenthesis, and then again, you put braces. Okay, it's like the null set, right? The null set, then put inside here, put that ordered pair, that one element, no, which is 1A. But there are other subsets. We can have, instead of 1A, 1B, or 2A, or 2B. But it's a one element set. No, we can have two element set, which are also subsets of this. We can have two. These two, we can include them. So you have two elements, 1A, 1B, 1A, 2A, 1A, 2B, and so on and so forth, because we can have 1B, then 2A, okay. And also three element set. We can have these three, 1A, 1B, 2A, or different order. It doesn't matter, same set, equal set. But to make it different, you choose other, like 1B, 2A, 2B, and so on and so forth. And also the 4. The 4 is also a subset to itself. Actually, a null set is a subset of this. Okay? So all of those are like, because when you say binary relation are a subset. So all of those possible to be binary relation. Okay? However, there's something in binary relation also. Okay? And that is, okay, let's see. Before that one class, we have what we call domain and range, right? Before we give examples for all of them, okay, we give examples for this and also for domain and range. So what is domain and range? Okay, I believe you know this already, right? The set of all values in the first set. Range is the set of all values in the second set. So we'll have examples, but I want to refer to the previous example to talk about domain and range. So actually, this is the domain, right? And this is the range in a way. Okay? But if you don't have this, just looking at this, just look at the first coordinate. So 1, 1, 2, 2. So the domain is 1, 2. You don't have to repeat it. No, 1, 1, and then 2, 2. No need. And then if you don't have this, then just look at again, the second coordinate, AB, AB. So AB. Okay, but this one class will be different, no? Interchange. You interchange them. So the domain now will be different. The domain will be this because you interchange them. Domain and then range. So it depends really on the set, on the relation that you have. Okay, so that's I believe you understand that part, the domain and relation. I'm sorry, domain and range, but you're used to like giving domain as the real numbers and then range as the found from the set of real numbers, right? But in this case class, we can have like not real numbers, the domain and range. Okay, so now let's have example. So again, these are numbers, no? So x 2, 3, 4, y 3, 4, 5, 6. Actually, here it's obvious now, right? But again, we don't have a relation here. No, we're just defining a set. We don't have a relation because a relation is a set of ordered pairs. So we'll have a relation here, class. But to get this relation, we have like a rule to get it, no? So again, we can x cross y, right? To get a Cartesian product. And how many elements will we have? If we do x cross y, how many ordered pairs will we get? So there's like a formula, right? 3 times 5, 15. 15 ordered pairs. And this is a binary relation of that because this is a subset of that Cartesian product. So in your notepad, as an exercise, you can list them down, no? Or later. Those 15 ordered pairs. So 2, 3, 2, 4, 2, 5, 3, 4, and so on and so forth. And this binary relation is a subset of that. That's why this is a binary relation. But the only thing different from the examples I gave a while ago is that randomly. But usually when you say binary relation, there's like a rule how to come up with this subset. And the rule is this. If x divides y, when you say x divides y, x is a factor of y. Or when you divide y by x, there's no remainder. So like this, 2 is a factor of 4, 2 is a factor of 6, 3 is a factor of 3, and so on and so forth. Or 4 divided by 2 is 2 without remainder. 6 divided by 2, no remainders. 3 divided by 3, no remainder. All of them. That's the meaning of x divides y. But you get the x from here, you get the y from here. Okay, that's how you do it. No? Actually, you do it one by one. And you get all of this. These are all the possible ordered pairs only. And this set is a subset of the Cartesian product of xy, not yx, x cross y. Because there are not equal sets, right? So if you would do it one by one, okay, 2, 3 cannot be because 2 is not a factor of 3. 2, 4, yes, because 2 is a factor. Yeah, that's how you do it. You do it one by one. 2, 5 cannot be. 2, 6, yes, because 2 is a factor of 6. And then 2, 7. So you have to do that pattern so that for sure you'll be able to list down all of them. You must have a pattern, no? A way, a systematic way. And then 3, 3, yes, you have 3, 3, and so on and so forth. Okay? So we can have a binary relation with a well-defined, meaning there's a rule. We can have a binary relation, like just get a subset of that, just like what we did in the previous examples. Now with this relation, or to be more specific, because we got this relation from these two sets, so we just call it binary relation, denoted as R, which is a subset of this cross product. No? We can talk of domain. No? The domain of this R is this. 2, 2, 3, 3, 4. But we don't repeat, so 2, 3, 4. The range, look at the second coordinate, 4, 6, 3, 6, 4. So this, 3, 4, 6. Customarily increasing, but it's okay, different order. You can have 4, 3, 6, 6, 4, 3, as long as they are all there. As I mentioned, they're still equal sets. It's just that the order does not matter in set. However, in ordered pair, the order matters. 2, 4 is different from 4, 2. Okay? So I think that's clear. That's the concept. No? Now, this is something interesting because here now we're starting to connect, computer science, no? Terminologies to algebra. Okay, like this sequence, no? Or the string. Usually, this is like more of computer science, not terms, no? Sequence, a special type of a function. So we connect it to an algebra concept, which is a function, which I just explained to you a while ago, right? What function is. It is a set of ordered pairs. It's a relation. It's just that when you look at the ordered pairs, all of them differ in the x values. If we're talking of that context of real numbers, no? X values, or if not in general, you can just say they're all different in first coordinate, right? The first coordinate, okay? Which the domain is a set of consecutive integers. So here, class, you're given the domain to be the integers, consecutive. So when you say consecutive, class, it's like 1, 2, 3. That's consecutive. 3, 4, 5, 7, 8, 9, 10, 11, consecutive. But if you have like 1, 3, 5, not anymore. Okay? Or even 1, 5. Even if there's a pattern, class, 1, 3, 5, there's a pattern. All of them are odd numbers. But still, it has to be consecutive integers. No? That one is consecutive odd. Okay, here, this one, class, is consecutive, as in the difference is only 1, like 1, 2, 3. If you subtract, the difference is 1, right? All of them. The two consecutive terms in the sequence. No? Okay, so their class, the range has to do with this, no? The string. Okay, so the sequence is a special type of function in which the domain is the set of consecutive integers. And then from this domain, we get a range, no? And that range can be a string over a finite set X. Okay, so a finite sequence of elements, so sequence, so meaning it's a function in which the domain is a set of consecutive integers of elements from X. So let's give an example. So example, you have this X, no? ABC, okay? And so we will get a string from here. So a string may be BAAC. There can be repetition, but we get it from here, or ACAB. So it's a string is what? Over finite set X. So this is finite because it's not infinite, okay? You can get the number of elements, 3. Okay, even if it's 100, 1,000, still finite, no? You can count them. A finite sequence, no? So this is a finite sequence, okay? String, a finite, because you can count it, 1, 2, 3, 4. Okay, where order is taken into account. So ABAC is different from BAAC, no? Now, repetition as a string can be specified by superscripts, no? like this. So this one can be written as b squared a cubed c. I believe you're familiar with this, no? Because in computer science, you use this term string, no? So anyway, that's like technical term. Now we can talk of null string. No, it's like null set. Okay, string with no elements. So indeed, similar to a null set, because when you say null set, there's no element. No, string with no elements indicated by lambda. And besides, it's really a set, because when you talk of string, it's a set, right? Okay, you go back. A finite sequence. Okay, but what is a sequence? Special type of a function. But what is a function? It's a set of ordered pairs. So it's still set. Okay, still set. So when you think of string, it's a set. Okay. String with no elements indicated by lambda. So instead of the null set, we indicate by braces, right? With no elements. But this one, since it's a different context, it's in computer science, instead of using grouping symbol, and in algebra, when we say null set, we use grouping symbol, the braces. But here, class, since it's in a computer science context, so we use Greek letter. We call it lambda. Okay, so if you see this, it's null string. Now, if you want, this one class are sets also. It's just that the difference is that in this set class, the set of strings over X, including the null string. So you include this in this set. It's like a set of whole numbers. In the whole numbers class, you have 0, 1, 2, 3, 4, 5. So 0 here is like the null. Okay. So this one is like a set of full numbers. This one class is like the set of natural numbers. When you say set of natural numbers without 0, so 1, 2, 3, 4, 5, 6, no? So this one class is the set of all non-null strings over X. So you don't include the null, the lambda. So it's like set of natural numbers, ano, the analogy, but still entirely different, no? Because there we talk of numbers. Here we talk of strings, and these strings consist of like elements, no? There are sets, they're not numbers, okay? Okay, to be more, yeah, length of string, lambda. The length of a string, I'm sorry, alpha. So we can name the string as alpha. You know, at this class, we distinguish the string from the elements. If you want to refer to a string, use Greek letters like alpha, beta, this one beta, a while ago, gamma, no? No, I'm sorry, lambda. But we also have gamma, no? Those Greek letters, there are a lot of them. But you notice for the elements in a string, we use what? English alphabet. But there are some literatures, they use string, letters for string. No? Okay, so as long as you're aware. No? But in our module, that's the distinction we do, no? Between the string and the element. No? But I just want you to make to be aware that in other materials, yeah, sometimes they use letters also for string. No? So anyway, so number of elements is string denoted by this. So I believe you're familiar with this. It's like absolute value. So it's like the number of elements in a set. Because a string is a set, right? So it's like, these are like the elements of the set. It's just like different notation. Because in a set class, we use comma, right? But again, that's what's interesting. Because you transition. Because computer language has its own language, right? Different from mathematics. But there is similarity, no? Yeah, this one can be repeated, but in a set, as much as possible, we want it distinct, right? In a set, distinct. But this one, they can be repeated, and in counting the length, in counting the number of elements, which is the length of it, you also consider the repetition, right? That's why this one, the size of, or the length, no? The length of a string is 5. You also count the repetition, consider the repetition. In a set class, no, right? No. Okay, this one class, you can use this superscripts, right? Because that's the purpose of using superscripts class. Just imagine, you write all the elements here, 39. No, it will be longer. So there's a reason for using superscripts. No? But we can make it shorter still. No? Later, you'll be able to find out. There's the thing like concatenation. Okay, later. So now this one is 39. You just add all the exponents. Okay, I think that's the next one. Yes, the concatenation. So we can denote string like this. Greek letters, you put them together, no, instead of just this, no. So this one class, we call it concatenation. So the string consisting of alpha followed by beta can be written as this. It's called their concatenation. So for example, this alpha and beta put together, but if you want to be more specific and you want a longer one, then all you have to do since alpha, A, B, then beside B, you write A, 3 A's, and then B, 4 B's, then 8, 32 times. You have to be consistent because you use here a longer one, but here you use superscript. But if you want to use superscript, you can put A squared, B, and then A cubed. Put them together. Now, if you want to make it shorter, just make it alpha, beta, no? Together. Then that process is called concatenation. Okay? Now, with that, notation, we can talk of what do you call this? Substring. It's like subset of a set. Actually, that's the essence, no? Because a string is a set, no? So substring. So look, you can see similarity. A string beta is a substring of the string alpha. If there are strings gamma, this is gamma, and delta with alpha equal to this. So indeed, class, you can see the concept of subset because remember this has elements, the alpha, and then the elements of alpha are the elements in gamma, in beta, in delta. Okay, so meaning to say subset because beta is like a subset of alpha because all the elements in beta you can find in this set. No, however, we denote set by capital letters, right? So again, I'm just telling you the similarity, but the proper way to look at it is string. So in the proper way, a string beta is a substring of the string alpha. So we don't say beta is a subset. No, I'm just making an analogy, no, for you to understand. Okay, because we denote sets by capital letters, but we denote string by Greek letters. But the essence is the same, right? The subset the same. Okay? So for example, if you don't want to use the Greek letters, or we can go to the small letters. So this one, what's the substring? AB. AB is a substring. ABA is a substring of this. Okay, it's simple as that. It's just that we put notations to make it shorter. No, we use Greek letters. Okay, class? I believe you understand what I mean. Okay, so that's substring. Now, let's go to the part 2. Okay, class? So for this one, class, I will use Google for examples. But for now, so this vector algebra or matrix analysis or the linear algebra, no? Okay, class. Why is it vector? Remember, in physics, there's what you call vector quantity and scalar quantity. So an example of that is the thing that you learn in algebra, the D is equal to RT, no? Or actually, the R there, class, is very general. Since it's distance, we're talking of speed. But sometimes you notice, you talk, instead of speed, you mention velocity. Are they different? Are they the same? In terms of this thing, algebra, no, or the vector, no, in physics, or as mentioned also here in linear algebra, there's a difference between that, no, the velocity and the speed. Because velocity is a vector quantity, speed is a scalar quantity. So what's the difference between the two? When you say scalar quantities such as speed, you don't mind the direction, just the magnitude, just the number. Okay, like 2 miles per hour, like that. So that's a scalar quantity. But if you mind the direction, a magnitude with direction, that's a vector quantity. An example of that is the velocity. It has magnitude and then it has direction, like 2 miles per hour westward, eastward, like that. Okay, and usually, class, if you want to be more mathematical, we denote it by like negative. No, we use signs. No, okay, negative, positive, like that. Okay, so here, class, we're dealing with those numbers, no, with those concepts in vector algebra. So we can think of matrix with like not just magnitude, but with numbers. I'm sorry, not just numbers, but with directions. But here, class, in this context, we will not talk about that. No, it's just that more specific what we will discuss. What I'm saying is put this in proper context, no, and that context is the vector algebra, no, meaning you're after the direction also. But for now, it's just the scalar. We're dealing with scalar. In fact, we have an operation called scalar, no, scalar multiplication. No, later when we talk about operation. So what is this thing about matrix? A rectangular array of data represented by capital letters. No? Just like the set, no? We use capital letters. But here, class, this is matrix, so capital letters. But for these capital letters, we have a different symbol. So we don't use the braces. or we don't use the parentheses. Instead, we use something like similar to brackets, but longer, vertically longer. Okay, not the smaller brackets, no. You notice the no, it's like short only. The height of the parenthesis is short. The height of the braces short. The height of the bracket is also short. However, there's similarity when we use it here later, no, in the matrix. It's longer, but there's a similarity in shape, no, similar. Okay, and then we put something inside, no, inside those longer brackets. Actually, we don't call them brackets, matrix symbol. We just call them the matrix symbol. But I'm just associating it with what you know already, which is the bracket. But we use bracket as grouping symbol when we want to group, right, numbers, letters in algebra. But here, class, we want to group. In this context, class, we use numbers. This array of data numbers for now, no? But we can have data which are not numbers, no, not real numbers. So to understand the concept, we deal with numbers first, no? So here we're talking of rows and columns. That's why we need taller brackets, no? Because we will have like rows of numbers, columns of numbers. That's why we have to make it taller, taller, no? To accommodate all these entries, no? Okay, it depends. It depends on the number of entries in your matrix. Okay. Now, if a matrix has a matrix A, so we can name it as capital letters. So A, for example, B can be B and so on. Has M rows and N columns, the number of rows M. So very general. N columns, no, the number of columns. Then the size of a matrix A is M by N. So again, very general. With examples, we'll make it more specific, no? It is either enclosed by parenthesis or bracket, no? So again, this one for notation of the size, no? So if you need to see this, meaning it's the size of the matrix A, the number of rows and columns, no? So this is what I mean, class, by bracket, no? But if you want to put all the entries, you have to make this taller, all the entries. But for this one, for notation of the size, no? And also this one we can use. Actually, the usual class subscript. We can also use subscript. You remember superscript? This one subscript for the size, no? But they also use this in some materials. Okay, class. So that's the size of matrix. Now these are the operations. So I'll use Google to discuss examples of this, no? But I believe even without specific examples, you can understand some of this, not like addition and subtraction. But still, I will use. Now these are the operations. We have addition and subtraction of matrices. It's like addition and subtraction of real numbers. But the thing here is that for matrices, there are a lot of numbers that we're doing, no? Dealing with. Now, it's like unlike addition, subtraction of real numbers, we can talk of just two numbers to add two numbers, three numbers, right? Okay, but here, class, we're talking of rows and columns. So we're talking of adding the numbers in the rows, adding the numbers in the columns, something like that, no? And subtraction. Scalar multiplication, there's a matrix, you multiply it by number. Like, for example, 2. You multiply 2 to each entry in the matrix. No? Okay, we'll have example to that later. Multiplication of matrices, you have two matrices, then you multiply them. How do you multiply them? But remember, in a matrix, you have a lot of numbers inside, right? It depends on the size. Then you have another matrix with a lot of real numbers also inside. So how do you multiply them? Simultaneously? How do you do that? Okay, we'll clarify that later. Transpose of a matrix, class, it's more of like you have a matrix, and then that matrix, class, the first row, if you want to get the transpose of that matrix, the first row will become the first column in the other matrix, in the transpose. Okay, the second row will become the second column. Okay, that's the concept. No, you understand this better with examples. Matrix raises to an exponent p. It's more of the concept is like exponentiation in real numbers. For example, 3 cubed. What's the meaning of that? 3 times 3 times 3. It's equal to 27. Here, class, there's similarity. Something like you have one matrix, you raise it to, for example, 2. So you meaning to say you multiply that matrix to itself 2 times. If you have 3 as p, 3 times. It's like a real number, right? For example, 5 cubed. So meaning 3 times 5 times 5 times 5. Here, instead of real number, matrix. And we represent matrix by letter. For example, capital A. So if you have A raised to 3, it means A times A times A. But matrix, huh? So that before you can understand this, you can find the answer. We have to understand this first, multiplication of matrices, because this one involves multiplication. And this one, class, is inverse of a matrix. No? This one is also interesting because this one is similar to the reciprocal. Remember reciprocal, for example, what is the reciprocal of 2/3? 3/2. But what do you notice? 2/3 times 3/2 is equal to 1. We have something like that here because there's what you call identity matrix. No? That if you multiply the matrix by its inverse, the answer is identity. That identity is like 1 in the real number. 1. It's 1 in a real number. But of course, this is matrix. So the identity here is in matrix form. Matrix, no? Not number. But the idea is similar. Okay? So there's like an analogy, no? Okay, but we need a specific example. But if we go to that, let me just read this general idea here. Addition and subtraction of matrices, it can only be made possible if the matrices are of the same size. Why? Because addition and subtraction are done by adding and subtracting corresponding entries respectively. So meaning they have to be the same size because you add and subtract corresponding entries. No? For example, if you have 2 by 2, you should add it to 2 by 2 also, right? Because you're adding corresponding entries. What if you add 2 by 2 and then you add it to 3 by 3? Not possible, right? Because how many numbers do you have in 2 by 2? 4. How many numbers do you have in 3 by 3? 9. Or how can you have the corresponding? They don't match, right? There's no matching. So that's why they have to be the same size. So you can have 3 by 2, add it to 3 by 2, something like that. No, same size. Now, scalar multiplication class, as I mentioned, it's like a matrix. You multiply it by a number. But the number, you put it outside. Like, for example, 2 outside, then you have a matrix. Then that 2, you multiply to each of the entry. It's simple. It's simple as that. No? That's why you can think also of division here because you can think of division as multiplication, right? For example, in a real number, if you divide a number by 1/3, it's the same thing. I'm sorry. If you divide a number by 3, it's the same thing as multiplying the number by 1/3, right? Divide by 3 is the same thing as multiplying by 1/3. So in a way, no need to talk about division because it's absorbed by this multiplication process. Actually, it's similarly for addition class. It's okay not to talk about subtraction because you can change subtraction to addition, right? For example, 8 minus 5 is the same thing as 8 plus -5, right? So anyway, now multiplication of matrix. This one is also interesting because to multiply any two matrices, you may ask, do they have to be the same size? No need. But there's a requirement. Oh, look at this. They're not the same size, but it's fine. You can get an answer. The requirement is this. Oh, look, the same. No? What is this thing? They have the same. If you multiply this set, this matrix by this set, the number. This one refers to what? The number of columns, right? So the number of columns here should be the same as the number of rows here. That's the only requirement. But of course, if the same size, still possible, right? Because if the same size, for example, 3 by 3, 3 by 3. Okay, because 3, 3. That's what I mean by the same size. I'm sorry. It will only apply for square matrix. When I say, there's a term square matrix. When I say square matrix, it has to do with the same number of rows, the same number of columns. But it cannot apply for all the same sizes. For example, if you have 3 by 2, 3 by 2, same size, not possible. You cannot multiply that because you notice different. 3 by 2, 3 by 2, 2 and then 3, not possible. But for square matrices, possible. 3 by 3, 3 by 3, 2 by 2, 2 by 2, okay, no? But the thing here is that as long as these two the same, no? It doesn't matter whether square or not square matrix. Again, when I say square matrix, it's not defined here. When I say square matrix, the same number of rows, the same number of columns. Okay, to multiply any two matrices, the number of columns of the first must be equal to the number of rows of the second. So a matrix with size 3 by 2 multiplied by a matrix with size 2 by 3 yields a matrix, possible. And in fact, the result will be the one left, 3 by 3. Okay? So if you make it 2 by 3, 2 by 3, the other one, 3 by, yeah, you can interchange the two, ano? But the answer will become 2 by 2. For example, instead of 3 by 2 times 2 by 3, you make it what? You interchange the 2. 2 by 3 times 3 by 2. The answer will be 2 by 2. That's why if you notice, you just interchange. But different answer. So you notice the commutative will not apply. So we can say that matrix multiplication is not commutative because a 3 by 3 matrix definitely is not the same as 2 by 2. Okay? It's not like a real number, right? In real number, real numbers are commutative because 2 times 3 is the same as 3 times 2. But in matrix multiplication, not possible because of the property. Did you get it, class? For example, we have two matrices. One is 3 by 2. The other one is 2 by 3. If you multiply these two, according to the rule, the answer should be 3 by 3. That's the rule. And this is okay to multiply because the same. If they're not the same, you cannot do that. Okay. Now, what if I interchange the two? Instead of this by this, I do it like this and this. Also, okay, we can get the answer. 2 times 3, 2 by 3 multiplied by this. But the answer will be 2 by 2. So different from 3 by 3. That's why matrix multiplication is not commutative. But we will not discuss here properties, no, of multiplication, because in the first place, probably some of you, how do we multiply, right? We're talking already of properties. Okay, don't worry. We will go to that later when we Google. Now, transpose of a matrix. This one is easier. I think I explained this a little while ago. If the entries in the rows and columns of matrix B are interchanged, then the symbol, we use this symbol, no? This one is used to denote the transpose of a matrix B. I explained this a little while ago, right? Let's give example later. Now, matrix registers an exponent P. I also give like a little explanation a while ago. Is equal to the matrix product where the matrix M is multiplied to itself P times. No? A later example. Actually, class, this is, if you know matrix multiplication, you can understand how to do this, right? Because this is multiplication. It's just that not only 2 times, can be 3 times to itself. Okay? So again, if this is matrix multiplication, you have to follow the condition. It has to be conformable. That's the term. They have to be conformable. No? You have to follow the conditions here because this is also, what is this? I'm sorry. Multiplication. However, class, definitely it will be followed because you're multiplying to itself, right? Multiplying to itself. Where is that? This one. You're multiplying to itself. Okay. So anyway, let's move on. Yeah, this is the last topic, no? Inverse of a matrix. This one class, we have a method, a manual method. However, it's long, so we will not discuss that. If you're interested, you can Google that. But there's a formula to get the inverse. Okay, especially for the 2 by 2, 3 by 3. But I think we'll just tackle for the 2 by 2 matrix. Okay, class. I remember I told you about the inverse. It's like reciprocal, meaning to say, if you get the inverse of this, you multiply the 2, the answer will be identity. The identity class for 2 by 2 is 1, 1, 0, 0. So 1, 0, 0, 1. For a 2 by 2 matrix, no? The identity matrix for a 2 by 2 is that. All the diagonal elements are 1, the rest 0. Now, if you have 3 by 3, you have 3 ones on the diagonal, the rest 0. So in multiplication, the identity is 1, right? But in matrix, we have the identity matrix, no? So where the diagonal elements are 1, the non-diagonal elements are 0. So it's like 1 in real number. So any number multiplied by 1 is the number. Same thing here, class, in matrix. Any non-zero matrix multiplied by identity matrix is equal to that matrix. So that property holds, right, in the matrix. But the commutative, no, it doesn't hold, right, for matrix multiplication. Anyway, these are just some properties. I'm just associating to the concept that you know already in high school, the set of real numbers. But again, they're different. There are differences, okay? Just like in the matrix multiplication, the multiplication, the commutative additivity in multiplication in the set of real numbers holds true. However, in the matrix, no, right? So anyway, so I think that's the end of it. However, as I mentioned, I would like to give examples using so I'll share to you this time around to discuss examples. Okay, so there. Okay, so let me, I think I have here already in the previous class, I used this. Okay, did you see the identity matrix? Okay, this is a 3 by 3 class, no? So you notice all the diagonal elements, no? Now, if you multiply this by 3 by 3 also, no, any non-zero 3 by 3, you will get the same answer, like AI is equal to A, something like that. So there's similarity to set of real numbers, no? Now, this is what the inverse class, the inverse, we denote the inverse by this -1. No? If you multiply this, it's equal to identity matrix. So it's like this in real numbers, right? The reciprocal of 1, 8 is 8. So multiply this, it's equal to 1. But of course, these are matrices. No? I think we have, do we have example? Yeah, this one is the 2 by 2 class for the formula. No? So there's a formula to get the inverse. Okay, this is the formula. This is the determinant, the AD minus BC class, right? Remember? By the way, going back, did I read that part? Let me read this part for a while. No? It exists if and only if the matrix is invertible. That is, the determinant of a matrix is not equal to 0. Okay, and that determinant, the one I showed to you a while ago, the AD minus BC. So if the determinant, I think the determinant, you heard it in high school, when you solve system of linear equations in 2 variables, remember, you have substitution, elimination, but there's this method, determinant. I don't know if you discuss it. So if, class, this is not the determinant in in another, there's like a determinant also, right? In the square root of b squared minus 4ac. The nature of the roots, no, it's different, no? But we have this determinant also in algebra, but different from that, b squared minus 4ac regarding the nature of the roots. Remember the quadratic formula? We have the quadratic formula, right? Remember that? The one with the negative b, right? Plus or minus square root of b squared minus 4ac all over 2a. The one inside the square root, the b squared minus 4ac, we call it determinant, right? To determine the nature of the roots. No, this determinant is different. This determinant for this square matrix, it's this, AD minus BC. Just multiply this, then subtract to this. So that's what the determinant in matrix. So the same term, but different meaning. But there's part in algebra when we talk of that context of solving system of linear equation. Yeah, we talk about this determinant. It's the same thing here, no? I don't know if you discussed that. Now, what we're saying is that if the matrix is invertible, or another term is non-singular, then there is an inverse. How will you know it is non-singular or invertible? If you get the determinant, it's not equal to 0. However, if it's equal to 0, meaning to say not invertible, not singular, okay? Or singular, meaning it's singular, because invertible means non-singular, right? But if it's not invertible or not non-singular, then it's singular. So if it's singular, meaning to say, never mind the terms, class, just think of it, the determinant. So if it is equal to 0, there's no inverse. If it's not equal to 0, there's inverse. Okay, let's tackle that here. It will become clearer here. So for example, this one, class, what is the determinant of this? Look at that. 4 times 6, 24. 7 times 2, 14. So 10. So there is. Because of that, there is. Indeed, there is. Oh, this is the This is the inverse. How did you get that? There is a formula. But there is a manual method also, which I will not teach you already because it's a long process. But you can study it, you can Google it. But for now, it's enough that the relationship, this relationship, it's equal to identity matrix. So look, so this is the inverse of this is this. Now using matrix multiplication. By the way, class, the matrix multiplication, you just do it this way. This one times this. The result is 1. This one times this is this. Where is that? This one. So 4 times 0.6 is this. 7 times 0.2, negative 0.2 is this. And add them, you get this result, 1. No? And then to get the other one, the 0, this one times this. So this is the 1. Oh, that's how you do matrix multiplication, class. No? That's how you do. Then if you want to get the entry here, the 0 here, 2, 6 times this. Okay, and this is the 1. Okay, let's make it bigger. Okay, class, did you get that? Now, if you want to get the 1 here, this 1 times this. So this is the 1. You get 1. And indeed, this is identity. And it is commutative, class. Meaning to say, if I do like A inverse times A, it's still identity. The answer. It's still true. It's still true. Okay. Now, again, to get the inverse, you have to apply the method, this method. So, for example, you're given this. If you want to get the inverse, interchange this to dA, and then get the negative. Okay. And then once you have that, get the 1 over A. This is the determinant. How do you get the determinant? AD minus BC. So if you apply it here in the exam, here, specific numbers, yeah, you can get the result. Class, this is the scalar multiplication. Scalar. 1 over 10 times 6 is 0.6. 1 over 10 times negative 7 is negative 0.7. Okay, now this is scalar. So with this one, we can see all the operations already. Actually, the two, multiplication and scalar. Okay? For addition subtraction, class, that's easy to understand. Corresponding entries. Corresponding. Okay, let's try. To Google. What is that again? Addition, subtraction. Actually, we can just talk of addition, addition of matrix. Okay. Yeah, addition. Actually, we can have calculator. So it says here addition of matrices is commutative. Yes, but multiplication of matrices is not, right? Unlike in set of real numbers, still commutative, right? So there's still difference. So anyway, this one easy to understand, the addition of matrices. No? Corresponding entries only. So this one is article, I guess. Usually Khan Academy is what? Like there's a video. Probably there's a video here. Yeah, no, we have and also we have like a text here. So it's easy to understand, no? Just by entry, corresponding entries. 4 plus 1. Okay, look. I recommend Khan Academy class. No? That's a good website to study mathematics. No? So A plus B. No? So 4 plus 1, 5. 8 plus 0, 8. That's all. Corresponding entries. Now, if you want multiplication, the same thing. 4 minus 1, 8 minus 0. Okay, so that's easy to understand. No? The addition. Okay, the addition, subtraction of matrices. No? So here we have subtraction. No? So that part is easy to understand. Now, this is the scalar. Okay, the scalar, you can think of it like addition 3 times, but you can think of it as like this. Now, 3 times 4, 12, 3 times 8, 24, 3 times 2, 6, 3 times 1, 3. Okay? You can think of it that way. Or you can put it in terms of addition, right? The same thing in numbers. Okay, class? So I guess you understand that part. Now, class, for the exponentiation, exponent, it's like the multiplication also, no? Multiplication. So let me, actually, operations, what's that? The transpose, you know already how to do it, class, right? The transpose. Let's go first to the transpose. So we do it randomly, class. Anyway, I already discussed with the PowerPoint, so I believe you understand. Yeah, this is easy to understand, the transpose. But let's have example. Yeah, it's like this, class, but it's still general. But you notice it's blurred because of this. So if you go to this, still general. I want this. This one is good. This one is first row. 2, negative 9, 3. It will become the first column here. Okay? So 13, 11, negative 7 will become second column. Okay, that's all. That's why if this is what? 4 by 3, if you get the transpose, it will become 3 by 4, also interchanged. No? So that's a transpose. We have properties of transpose, but we will not tackle that. No, that's a transpose of a matrix. So you know already inverse of a matrix. Yeah, and also the multiplication. But I want to discuss more on the multiplication. If we have multiplication of matrices, we can even have calculator, meaning to say you don't have to do it manually. So there's technology. What is that? Matrix multiplication. So there we even have calculator. So matrix multiplication. I think this is fine. Let's see. There's an article. Though there's also video, no? Oh, okay. This one, that's one is scalar. Where is the no? I want to have like it's kind of general. General class that you have to answer. Actually, this one class, for example, 1, 7 times 3, 5. That's how you do it. So what is 1 times 3? 1 times 3, 3. 7 times 5, 35. Plus 3, 38. That's how you do it. No? It's like first row, first column. So you will get the 1, 1. The 1, 1 here. No? So 38. So 1, 7 times 3, 2. So what's 1 times 3? 3. 7 times 2, 14. So 14 plus 3, 17. So that's how you do it, class. So now you will understand why they have to be the same, right? The number of columns should be the same as the number of rows because you have to do the matching. No? So if you have 2 here, 2 columns, you should have 2 rows because you have to match 1 to 3, 7 to 5. So just imagine if you have 3 columns here, 3 rows. Or how will you match? How will you multiply 1, 7 by 3 rows here? 3, 5, 5. No match, no? That's why there is, you need that requirement, class, no? The one we mentioned, no? In the matrix multiplication, right? That this one the same, 2, 2. Because of that, that process in multiplication. Now, class, the this one class is the same as matrix multiplication. It's just that p times. Okay, not only 2 times, 3 times, but the same. Usually, you can apply this class to what? Square matrix, meaning the same number of rows, the same number of columns. Okay, square matrix. This one. Okay, I think you understood, na? Okay, so that ends the lesson for this week class. Thank you very much for attending. So bye for now.